Welcome. Today we're going to talk about derivatives of logarithms. Now logarithms can be a little scarier, but their derivatives are actually easier. So first we're going to find one, and then show all the formulas, and then we're going to do a couple examples and see how they actually work. So first we're going to find the derivative of the natural log in a manner similar to the way we did it with inverse trig. But you don't have to remember that, because what we're going to do is we say y equals ln x. What I want to do is take the derivative of the ln x, but I can't because I don't know what it is. But I do know that if I take e to the y, which is then e to the ln x, I have just x, because e to the ln x is just x. So I have e to the y is x. Now I can take the derivative, because the derivative of x is 1. The derivative of e to the y, well, y is a function. It's an internal function to this. This is e to the stuff, and we know the general rule of exponentials. The derivative of e to the stuff would be e to the stuff times the derivative of the stuff. And we like this because it gives us the derivative of the stuff, and the stuff was y. So we have a y prime. Now, what do we do here? We want the y prime, so we just divide. Y prime is just 1 over e to the y. That would be enough if we wanted to answer in terms of y, but we don't. We want the derivative in terms of x. But we know that e to the y is x. Hence we get y prime is just 1 over x. Hopefully you can see this is really not that bad, and the formula is very, very simple. Take a look at that. The derivative of the natural log of x is 1 over x. Where'd that come from? Well, this is where it came from. But it's very surprising. It's very surprising that the transcendental parts of this, the logarithms, are gone. Just 1 over x. Anyway, ln x's derivative is 1 over x. If we use a different base, remember if we use other bases, it gets a little mushier, messier, and it is. The derivative of the log base b of x is 1 over x ln b. We did this one before once, but just in case, the derivative of b to the x is b to the x times ln b. So these are similar. Notice they're kind of the same. The derivative of e to the x is not on here because its derivative is still just e to the x. But if it were, well, that's what it would be. And then one last one, the natural log of something, stuff. This is a generalized logarithm rule. So its derivative is 1 over the something times the derivative. This is the chain rule. Or if you want, because this is a fraction, we could pull this up here and just get the derivative over the original. Here are the rules we use. Let's try some examples. There are 4 examples this time. 3 there, 1 here. Take a look at them, try them out. I'll give you a couple seconds. Okay, hopefully you were able to work them out, pausing obviously in between. But what do? You take the derivative of ln of stuff. This is just that last rule. So I can even apply the last bit. It's the derivative of the inside, which is 2x, over the inside. I'm sorry. Yep, that's exactly it right there. Now, you might have wanted to say 1 over x times 2x. That would be wrong. This is not multiplication. There is nothing multiplying in these parentheses. That's composition. You've got to be very careful what parentheses mean. And in this case, it means ln of x squared plus 1. The of is the chain rule. And so we use the chain rule form right there. How about this one? This is x squared times ln x. The times means we use a product rule. Product rule. The derivative of x squared times the second thing, which is ln x, plus the derivative of x squared. I'm sorry, the derivative of ln x, which we know is 1 over x times x squared. We are not done here because we can simplify. Notice, 1 over x times x squared, that's a fraction x squared over x. That simplifies as x. So we rewrite that. I have 2x ln x plus x. You could further write this as x factored out to ln x plus 1 by pulling the x out of the whole thing. Sometimes that's useful, but honestly, if it's a choice between these two, I kind of like this one better. I think it looks prettier. If you like this one better, that's fine. One of these two is simplified. Either way. Let's try this. Let's tackle this one now. It's a quotient. So we have to use the quotient rule. When you take the derivative of a quotient, it's the derivative of the top, which is 1 over x plus 0, times the bottom, minus the derivative of the bottom, which is 1, times the top over the bottom squared. Now you might be quick in thinking, I'm just going to cancel the x's here. You can't, because there's a minus. These are two different terms. You have to simplify the top before you can do anything with it and the bottom. Now, simplifying, I've got 1 over x times x. Hopefully you can see 1 over x times x is 1 minus ln x minus 1 times that, so minus 1 over x squared. And now, hopefully you can see there's still one more step, 1 minus 1. I get minus ln x over x squared. That's my final answer. Now there's one more up here, 3 to the log base 3 of x. And if you think about it, maybe you can find a simpler way to do this, but I'm going to do it with the rules. It's 3 to the stuff. I didn't write a rule for b to the stuff, but the derivative is the chain rule. It's going to be the derivative of 3 to the x, which is, 3 to the stuff, which is here, ln 3, that's the derivative of the 3 part, times the derivative of this piece. The derivative of this piece is 1 over x ln 3. Now, I didn't leave much space for this one, but there's a reason for that. This is 3 to the log base 3 x ln 3 over x ln 3. That's all those pieces. The ln 3's do cancel, because this is times. So divide it out, divide it out. More though, 3 and log base 3 are inverse functions. So the 3 to the log base 3 of x is just x. So I get x over x, which actually simplifies more as 1. Now it may seem surprising that all of that disappears as 1, but it shouldn't if you remember that 3 raised to the log base 3 of x is just x. So all I'm asking you for is the derivative of x here. The derivative of x is 1. If you had realized that first, it would have been a lot easier. But then you wouldn't have had as much practice, and practice is good. Until next time, this is Dr. Jed.